Good day mga ka-CE. This video is all about surface and subsurface runoff phenomenon, which will focus on the different flow routing techniques including first, channel routing, second, hydraulic routing, third, infiltration and percolation, processes and movements, and lastly, groundwater storage and the flow of water. So to start, let me first differentiate surface runoff from subsurface runoff. So, surface runoff refers to the rainfall, snowmelt, or irrigation water that flows over the soil or land surface toward the stream water. On the other hand, subsurface runoff refers to the flow of water towards the stream channel that occurs below or within the land or soil surface. It is basically slower than the surface runoff. So, to elaborate further, here is Kaina Fermanes to discuss about channel routing.
Channel routing, masking method, and reservoir method. The change in the shape of a hydrograph as it travels down a channel is studied by channel routing by considering a channel reach and an output hydrograph at the upstream end. Information on the flood peak and duration of high water levels obtained by channel routing is of utmost importance in flood forecasting operations and flood protection works. In channel routing, the storage is a function of both outflow and inflow discharges, and hence a different routing method is needed. The flow in a river during a flood belongs to the category of gradually varied and steady flow. Storage in channel reach. Prism storage. It is the volume that would exist if the uniform flow occurred at the downstream depth. The volume formed by an imaginary plane parallel to the channel bottom drawn at the outflow section water surface. The prism storage is similar to a reservoir and can be expressed as a function of the outflow discharge. Wedge storage. It is the wedge-like volume formed between the actual water surface profile and the top surface of the prism storage. The wedge storage can be accounted for by expressing it as SW is equal to F times I. Masking in reservoir method. Masking method provides a reasonably accurate results for moderate to slow rising floods propagating through mild to steep sloping watercourses. In the masking method, the storage S in the routing reach is represented by the following discharge storage equation. S is equal to K times X plus 1 minus X times Q, where K and X are coefficients and M is a constant exponent. It has been found that the value of M varies from 0.6 for rectangular channels to a value of about 1.0 for natural channels. Reservoir method. When X is equal to 0, the storage is a function of discharge only reduces to S is equal to KQ, wherein the coefficient K is known as storage time constant and has the dimensions of time. It is approximately equal to the time of travel of a flood wave through the channel reach. Such storage is known as linear storage or linear reservoir. To use the masking equation to route a given inflow hydrograph through a reach, the values of K and X for the reach and the value of the outflow Q1 from the reach and at the starts are needed. The procedure is described as follows. Number 1. Knowing K and X, select an appropriate value for the change of T. Number 2. Calculate C0, C1, and C2. Number 3. Starting from the initial conditions 11, Q1 and known 12 at the end of the first time step, change T, calculate Q2. And lastly, number 4, the outflow calculated in step C becomes the known initial outflow for the time leap. Next line step, repeat the calculations for the entire inflow hydrograph. That would be all. Thank you for listening.
Hello, my name is John Kenneth D. Escalante. I will be reporting hydraulic routing. Routing is a technique used to predict the changes in shape of a hydrograph as water moves through a river channel or a reservoir. In flood forecasting, hydrologists may want to know how a short burst of intense rain in an area upstream of a city will change as it reaches the city. Hydraulic routing. There are certain flow condition situations where hydrologic routing methods may not be appropriate. When this is the case, hydraulic routing calculations are required as flow conditions become more complex. Hydraulic routing is based on the solution of partial differential equations of unsteady open channel flow. The equations used are the Saint Bennett equations or the associated dynamic wave equations. Hydraulic routes. A geographic example of hydraulic routes obtained from a specialized computer software. These are the equations involved in the computation of hydraulic routes. Under more complex flow conditions, hydraulic routing must be used to calculate downstream flow, stage, or velocity when given an upstream hydrograph. Recall that hydrologic routing uses the continuity equation, which preserves the water volume in the channel. Hydraulic routing, on the other hand, uses the continuity equation and adds an energy budget approach, represented by the momentum equation. In this way, hydraulic routing accounts for the actual physics of water movement in the channel. Methods to compute. Some approaches for solving the momentum and continuity equations together include using dynamic wave equation, making simplifying assumptions, and then solving either the diffusion wave equation or the kinematic wave equation. The National Weather Service has developed various computer programs for modeling hydraulic routing. FLDWAV, pronounced flood wave, version 2.0.0, released in June 2000, handles very complex flow situations. When to use hydraulic routing? As mentioned earlier, examples of the stream flow conditions that will need to use this type of routing include very small slope streambeds, tidal influence streams, flash floods, including dam breaks, or any situation with rapidly changing water depth. Hydraulic routing advantages. Because it uses the actual physics and energies involved, the hydraulic approach offers two important advantages: higher accuracy for calculated water depths, better representation of many special flow conditions, including backwater effects, physical structures, and unsteady effects. Hydraulic routing disadvantages. There are some important disadvantages of hydraulic routing that need to be kept in mind. Three key disadvantages are: specialized computer software is needed to solve the more complex equations. There is a need for extensive data to describe the channel topography and cross sections. This is a numeric method, so there are situations where the underlying equations may produce unrealistic or undefined answers. A brief summary of hydraulic routing. Hydraulic routing is best for tidal influence river reaches, dam breaks, shallow slope rivers with backwater effects, while more accurate results are possible with hydraulic routing methods. A downside is much more data is required. Hydraulic routing methods can produce unreasonable results and can only be used under special flow conditions. Thank you. That is all for my report.
Hi everyone, this is me again, Raiza Meiji Escote from BSE 3B, and I will be reporting about infiltration and percolation as well as its processes and measurements. So, again, to start, let us first differentiate infiltration from percolation. So, infiltration is the process by which water on the ground surface enters the soil. It is also caused by multiple factors, including gravity, capillary forces, adsorption, and osmosis. Many soil characteristics can also play a role in determining the rate at which infiltration occurs. On the other hand, percolation is the movement of water through the soil itself. Finally, as the water percolates into the deeper layers of the soil, it reaches groundwater, which is water below the surface. The upper surface of this underground water is called the water table. Now that we already know the difference between percolation and infiltration, let us now define infiltration rate. So, what is infiltration rate? Infiltration rate is a soil infiltration rate, known as IR, is the volume flux of water flowing into the profile per unit of soil surface area under any set of circumstances. In simpler words, It is a measure of how fast water enters the soil and is typically expressed in inches per hour. For initial in-field assessments, however, it is more practical to express the infiltration rate as the minutes needed for a soil to absorb each inch of water applied to the surface. Next, let us define what is infiltration capacity. So, infiltration capacity, denoted as F, is the maximum rate at which a soil is capable of absorbing water in a given condition. It tends to decrease as the soil moisture content of the surface layers increases. It also depends upon such factors as grain size and vegetation cover. Next, here are the factors affecting infiltration. So first, the land surface. Next is the land vegetation cover, the surface soil characteristics, storm characteristics, surface soil and water temperature, and lastly, chemical properties of the water and soil. Now, let us proceed to the measurements of infiltration. So first is the area measurement, next is the point measurement, next is the estimating infiltration rate, next is the Horton infiltration, the Phi index method, the Philip method, and lastly the Green Amp method. So now you can just pause the video and take time to read it because I will no longer read it for you as well as to the other slides. So that is all for our report. Thank you for paying attention and happy vacation, everyone.